Okay, our last speaker of this session is Professor Jonathan Leach from Heriot-Watt University.
Well, first of all, I'd like to thank the organizers for a great opportunity to talk at such an interesting meeting. My name is Jonathan and I work at Heriot-Watt University, and I'd like to talk to you about some of the recent work that I've done on imaging with single-photon detector array technologies. Now, many of us as experimentalists in quantum optics will have used single-point detectors, whether superconducting or silicon detectors at room temperature. And there's a new technology of array sensors, and they have two very, very special properties. The first is they're sensitive to single photons, but then second of all, they have very, very high temporal resolution. So the question then is, what can you do with an imaging device that has single photon sensitivity and temporal resolution of order nanoseconds or picoseconds? So as part of the UK's quantum technology initiative, we've developed these sensors in collaboration with Robert Henderson at Edinburgh University. And packaged, they look like this. They look essentially like a regular camera with a lens on. If you look at the image on the bottom right-hand side, you can see that that's a picture of a 320 by 240 SPAD array, and that's what's inside that aluminium box there. So at the moment, these SPAD arrays come in two general forms. The first form is high spatial resolution, where we have something like 300 by 200 pixels, but the temporal resolution of those is quite low. So it's 10 to 20 nanoseconds gate. So your sensor's turned on and then turned off. And the on-off is of order tens of nanoseconds. And that gives you your ability to localize in space where light is. The second version is low spatial resolution, so only 32 by 32 pixels, but then each pixel has TC/SPC technology associated with it, so that's time-correlated single-photon counting, and there the bins associated with the histogram are of order 50 picoseconds. Now, what's exciting about that is if you convert a 50 picosecond bin into an effective frame rate, it turns into a camera that's now got a 20 billion frames per second frame rate. So the question is, what can you do with a frame rate of 20 billion frames a second? And one of the nice things is you can actually now film light in action. I should say that the design for these cameras is provided by Robert Henderson at Edinburgh University, and he has a long-standing collaboration with ST Microelectronics, who are a sensor company who have an imaging division in Edinburgh. They're actually a French company, and the fabrication of these devices is done by them. Now, there's a breadth of work in Scotland, and particularly at Heriot-Watt, on these. Daniele Faccio, who's now at the University of Glasgow, instigated the work on looking round corners. I've done work with him on light and flight imaging, and I'll talk about those both today. Rory Duncan, Paul Dalgarno, they're doing fluorescence lifetime imaging with these detectors. I have a long-standing interest in high-dimensional entanglement. It would be fantastic if we were able to use these sensors to measure position momentum correlations or do multi-photon coincidence measurements, and you can, but I think as Paul Couet was discussing yesterday, the stringent requirements on efficiencies when you do multi-photon measurements mean that the results for these SPAD detectors in their current forms with their current efficiencies are, I would say, work in progress towards being able to establish high-dimensional entanglement. And also what I'd like to talk about today is imaging and scattering media, and this is a collaboration that I've had with Gerald Buller, who's also at Heriot-Watt. So I think these next slides summarize what you see with a SPAD detector. A SPAD is a sensor that is a threshold detector. It sees the presence of photons, one or more, or not. And so in any sort of one frame that you see, you have a binary image. 2 frames, you can get more resolution, and then you start adding together multiple frames to actually get any bit depth. Now, this process can be done very fast, so you don't perceive it, but at the end of the day, these detectors are giving you ones and zeros, and then you process those ones and zeros in spatial locations and time bins to generate the data that you want to see. So this is work that Daniele and myself did at Heriot-Watt. I think it's one of the nicest videos showcasing the technology of these detectors. What you'll see is a pulse of light entering the frame from the right-hand side, and this pulse of light bounces off these 3 mirrors here, and this camera, this is done with a 32 by 32 high temporal resolution sensor, is able to see the pulse of light in air. So this box represents the field of view of the camera, and we're superimposing that with an optical image. So I'll play that again for you. So the obvious question that I often get asked here is, was that one pulse of light? And the answer is no, that's not one pulse of light. That was a 4 kilohertz laser that was sending out identical pulses of light, and we were taking multiple snapshots of where that pulses of light were at very, very precise times. Okay, so it would be really nice if we could do single-shot measurements, and people have been investigating that, but the technology at the moment is set up for repeated events, and that's why it's very nice for looking at pulsed lasers. So here's how that experiment in particular works. So we have a laser source which is sending out a pulse of light, bouncing between these mirrors, and the photons then scatter off air molecules, nitrogen and oxygen molecules, and then make their way to the camera. Meanwhile, a trigger pulse is sent to the 32 by 32 pixels, and that starts a stopwatch on every single pixel. So that's those stopwatches. And the stopwatches stop when they see a photon, and each pixel looks at a different point in the scene, so the stop comes in at a different time. And then when we play the data back to you, what we're playing back is the arrival times of the photons. So having published that work, we then went on to investigate supercontinuum generation in nonlinear fiber. You can see white light generation here. This is done with optical filters. We used 5 colored filters placed in at different times and then processed that data. And then this, I think, is a really nice demonstration. So this is a gigahertz laser from Derek Reed's group. And one of the nice things about a gigahertz laser is the spacing is 1 nanosecond in time. So you're seeing the pulses of light propagating through a fiber there, spaced by approximately 1 nanosecond. I should say that the width of the finite width of that pulse that you're seeing is associated with the jitter of the detectors, not the width of the laser pulse. Now, there are limits to the width of it would be very nice if we were seeing narrower pulses in time. However, the jitter of the detectors of order hundreds of picoseconds means that we see this this spreading. The next work was looking around corners. So this was a guy called Terry who liked to hide around corners. To give you an idea of how big he was, that's me there. Terry was deliberately white, although I have to say that we have gone on to do these experiments with human targets, and Daniele at Glasgow has now gone on to do very nice machine learning approaches for identifying different targets, different human targets. But the core idea is the following. So you take Terry, you put him behind a wall, and you take your camera with its field of view and a laser, pulse laser, and shine that laser onto the floor beside the field of view. Now, it's crucial that the field of view overlaps with direct line of sight to the object that you're trying to detect. Likewise, that the laser, which essentially sends out an echo pulse to the object, which then goes and hits the object. And as you can see, I'll try to go back one. As you can see here, the return pulse moves across the field of view of the camera. Now, what I want you to imagine there is that if Terry was positioned at the top of the screen, but still out of view, the shape of the return laser across the field of view of the camera would be different. So the shape that the laser sweeps across the field of view of the camera reveals the location. Okay, now you're only able to do this because of the temporal resolution of the camera. If you had a worse temporal resolution, then that nice thin line would be blurred out. And there's actually a very nice analog with the Rayleigh criteria about being able to separate two points by how the waves emitted from those points get to the observer screen. So here are the results. When Terry was down at the bottom left, we were able to record that red stripe there. We moved Terry round, and you can see that as long as Terry is quite close, we're able to record where he is. And me and my student, Susan, then went on to build a 3-point detector SPAD version of this experiment. It turns out you don't need the imaging device. You just need point detectors. So with 3 silicon SPADs, what can you do? What I'm going to show you now is a video where this board is moved along this track, and the real-time location of the object is plotted on the right-hand side. So the information on the left-hand side was not given to the computer and the imaging system. The best guess of the computer's location, or the guess of the object by the computer, is indicated by the stripe. So I'll play this for you here. So as you can see, as this target is moved around at 2 hertz, we were able to detect the object. If you look very closely, you can see Ryan underneath this box as he's moving it around. And really, it turns into a signal-to-noise issue the further away you go. The scaling is not particularly good. If you imagine me sending a laser pulse out to an object, there's a sort of door around there. I have no loss on the first laser pulse going out, but as soon as I hit the wall, I scatter and I make a sphere. And then that sphere goes and hits an object, and then it itself makes another sphere. And then that sphere then hits the wall again, and it comes back to me. So you've actually got 1 over r to the 6th loss. You get 1 over r squared every time you get that there. Which means that in practice, it's very difficult to see quite far round a corner, but you can see quite far out. So we've done tests at 50 meters out and 3 meters round a corner, but it would be very difficult to do 3 meters out and 50 meters round a corner, just because of the scaling. I want to move on to imaging and scattering media. Here's a nice example of why you might care. This is an example of a helicopter landing in snow, and this is taken on one of our field trials. Unfortunately, it was quite icy, so even though it was icy, we didn't see that much snow. And a day like today, the visibility would be very low. So any system that could provide pilots, or drivers, with assisted vision in degraded environments would be advantageous. I don't think with this technology we're going to be able to see through smoke or see through scattering through fog with 100% visibility. What we're trying to do is make small gains to improve the safety and to improve the operational lifetime at which you can operate vehicles. And the key idea is this, that we're going to do active illumination of our target, but because of the very, very high temporal resolution of our system, we can turn on and off our sensor corresponding to very precise depths, and therefore only take the return light at one particular depth, therefore increasing our signal to noise and being able to visualize. So we've done a number of trials. Again, Susan built this system. The SPC imager is the single-photon detector imager inside there, and we have a scanning pulsed illumination system. In the future, we hope that we can get the footprint of this detector down to something more handheld, but as you can see at the moment, the control electronics mean that it's sort of on a bench. Now, the target scene that I'd like to discuss and show you the results of is this here. It corresponds to a mannequin in front of a depth board at a distance of 150 meters away. So 150 meters away is a very relevant distance for the automotive industry. And you can see here, if you look at the photo on the top left, you can see the depth board and the targets that are separated by 10 centimeters in depth. And the first results that we have are this here. This is reconstruction of the depth of that target using a single-photon detector array sensor. I apologize for the lack of resolution on the image on the right, but you can see that color corresponds to depth now. The image on the left was just a photograph from a Nikon digital camera, and you can quite nicely combine these two to give a 3D version in color. Now, one of the nice things that we've been doing has been looking at data fusion approaches where you take the optical image and the information from your 2D optical image to improve the three-dimensional depth image. Now, for example, if you had an incomplete depth profile, this is artificial in this situation, but if the black areas there corresponded to information that you didn't have for whatever reason, maybe you were sampling at a low resolution, you can upscale that by taking your optical image and using the prior information associated with a scene. So if I ask you now, what is the depth of anything that is purple? I don't know if I can have a mouse, yeah. So this purple here, right, is very unlikely that you guys in the audience are looking at any other purple in this scene here that is at a different depth than this and this here. So with the prior information that colors are normally at the same depth to one another, you can improve the three-dimensional depth information. Okay, so I'd like to quickly show you our scattering media results. We've actually just returned from another trial with DSTL where we've massively improved these results here, but I'm not actually able to show you those because DSTL haven't quite approved them yet. So this is data from about 10 months ago. We're looking at this target here, the top right-hand side of this target, and we're looking at it in these conditions here. So you can see that with a very small amount of smoke, the image quality is massively, massively degraded. And we can record the number of attenuation lengths that we have in any particular situation, and look at the corresponding signal from our SPAD array sensor. So I'll work backwards in time. This is the image on the right-hand side corresponds to the optical image, and the bottom is the SPAD array image. So you have a very nice one-to-one correlation, and this is when in clear visibility. So that's what you would expect. And as we go backwards in time, we're getting more and more smoke. And you can see here that even at quite high scattering, we're able to record some image from the single-photon detector. As I said, we've actually improved these results significantly, but I'm just not at the moment able to show those results. Right, so in the last few seconds, I'll summarize. I've talked about high spatial resolution, low temporal resolution, low being lower than the best that we can get, and I've talked about low spatial resolution, high temporal resolution. And what we want really is the best of both worlds. We want high spatial resolution and high temporal resolution, and that's where the next generation of these sensors is going. One of the key changes to the next generation of SPAD sensors is that we have on-chip histogramming. So rather than feeding out bit planes and time tag data to a computer which then has to process, we actually get histograms sent to the computer with very, very low latency. So it's essentially a real-time sensor. And this is what the current version looks like. That's the latest SPAD sensor here. This is it. That's the sensor there. This camera over here is a Sony digital camera, which we're benchmarking our images against, and this is just a lens to form an image. What I'll show you here is the operation of the latest sensor at 25 frames per second at a distance of 50 meters. This is my student Max. He'll do a little dance for you. The image on the left is the 3D information from the sensor, and the image on the right is from the Sony camera. So you can see there's very, very minimal data processing done on this. If you were to look at the computer screen as this was happening, it would literally be what you're seeing on the left-hand side. And that's a massive change in terms of latency and performance. And that's such an important thing if you think of the automotive industry. You know, if a sensor like this is going to perform on a car, it doesn't matter that it was able to see a child an hour later. It matters that it's able to see a child and make a decision within a fraction of a second. What we're quite excited about is the next thing here, which is the ability of these sensors to perform at extremely high speeds. So now we don't have to see repeated events. We're seeing in 3 dimensions at high speed. So the image on the left is taken at 300 frames per second. The one on the right is from the Sony camera. That's 1,000 frames a second. And I'll play this for you here. So you can see the ping pong balls at different colors. Interestingly, at one point, one of the balls goes in front of the laser, and then the signal to noise just is terrible. I think it's coming up soon. Right, so that's the point there where the ball goes in front of the laser, and you therefore don't have any return, or no illumination. And then lastly, last video here is a, let me just pause this. This is a fan at an angle with, again, ping pong balls. So the first video, this one here, this is in real time. The second video is the slow motion, and then the third one is our SPAD array data. So that's it in real time. This is the 1,000 frames a second. And one of the things that we're going to be pushing in the future is how to upscale our 3D data with the prior knowledge and information from the optical image. So here you can see our SPAD sensor data. The hands are different colors, the balls are released, and the balls are different colors. So you're actually able to see things in slow motion at high speeds. Okay, I'd just like to advertise my website if you're interested in any of the publications. If you go to hwquantum.org, don't go to hwquantum.com, something else. I tried it this morning. It was some Chinese gambling website. So hwquantum.org, and you can find any of our publications there. Finally, I'd like to thank the sponsors, EPSRC, DSTL, and we're part of Quantic. My team, Susan's done an awful lot of this work. Feng has helped out too. And thank you very much to you guys for the chance, or sorry, for listening. Thank you.
Any questions?
Just real quick, you didn't mention the wavelength. Is this at 1064?
Okay, so yeah, it's a very good question because it very much depends on your ability to see through scattering. So our experiments were done at 670 nanometers, so not the best wavelength for seeing through scattering. We're using that through availability of lasers. And the sensor itself is a silicon sensor, so it won't see that much beyond 1 micron. Gerald Buller has been using 1.5 microns, and that performs very well through scattering media.
And then the follow-up would be that how do you shield against the background light?
There's a filter in front of the camera, a notch filter. It turns out that it's quite difficult in lots of scenarios. The solar background's quite bright. You can do background subtraction, you can take frames, but we're left with putting in filters and doing sort of initial images and taking that away. For the looking around corners one, it's quite an interesting one. You don't actually need to do that much background subtraction because what you're looking for are differences in signal. So the difference of and changes, you're doing one thing minus the other, so the background automatically is subtracted. So it doesn't really matter too much in that case.
Yeah, I think. Oh, one quick question.
So beautiful work, and I guess this is quantum in the sense that looking at single photons. Have you considered, are there any interest in doing things with entangled photons in this type of detector capability?
Yeah, so as I mentioned, I have a long history of measuring high dimensional entanglement. I've done lots of work on orbital momentum entanglement and recently published on OAM swapping, entanglement swapping. We are currently looking at how these detectors can be used for measurements of high dimensional entanglement. I would love to talk with you more. I could show you our recent results on this. What we're finding is because the efficiency, when you consider the fill factor and the efficiency of the silicon, each pixel has an effective efficiency of about 10%. And when you combine that with the dark count rate, it means that your performance is not quite as good as two silicon SPADs that you would buy off the shelf. And then when you multiplex this with all of the pixels, you're able to classify and quantify entanglement, but it's not very high dimensions. Okay, but yeah, it's a very interesting question. I can happily show you our recent results as well.
We don't don't have time at this point, but certainly come up here at the break. But thank Jonathan again.